Hello and welcome to another MS365 tutorial. I am excited to talk to you a little bit today about dealing with imbalanced data with classification models and how to handle those when you're working with data analytics and machine learning. So today we're going to be working with that diabetes data set that we've been working with on and off throughout the semester. If you're with me in class, you can download that data set from Canvas. If you are working along online and you just fumbled across this and you need some help, honestly, it's pretty easy to find. If you go out to Kaggle, you can Google diabetes data set, and it's pretty easy to come up with. And actually, you know what? Let's just jump out of this PowerPoint and go into Google Colab for a second, and I will show you that data set. Oops. Maybe, just maybe. All right. Bear with me today, friends. I'm a little sick. I'm getting over a cold, so I've lost my voice a little bit, but I always like to get a little something out before homework is due. So what I'm going to do is jump into my Google Colab here. I'm going to take a peek at my Google Drive and find our diabetes data set. And the first thing I'm going to do is I'm going to read that diabetes data into a data frame. And let's just take a look at the data. So if you're not familiar with the diabetes data set, it is a classification model that tries to determine or tries to predict if you will have diabetes or if you have diabetes based on all of these different predictors, pregnancy and glucose and blood pressure and all these different things. So ultimately, all of these are your predictor values, and your labels, aka your targets or the things you're trying to figure out, is going to be outcome. And you've got this in both text form, like as a string, and just as binary form. So 1 means you got diabetes, 0 means you don't have diabetes, right? Because this is our historical data. So one of the things I'd want to do when looking at my labels or looking at my target values when I'm creating a model, if it's a classification model, is I'd want to take a second and look to determine if my classes are balanced. So let me just show you what that means. So I'm going to jump in and I'm going to look at my outcome text. And what we want to do is just look at our total values per class. So what's that going to look like? It's going to look like this. So I have 2 classes in my data set. I have normal people and I have people that have diabetes, right? So in my historical data, that's what we've got. So what I see when I look at this is that the classes are imbalanced, right? So I've got 2 classes, normal and diabetes, and there are 500 that have normal, 268 that have diabetes. This is class imbalance. That is not good. Classification models don't play well or don't do well or perform well when you're dealing with imbalanced data. So that's what I want to talk to you about for a little bit, and I want to show you some ways to fix that. So let's go back into that PowerPoint for a second. Oh, let's switch our displays and talk about it a little bit. So here's our data set that we just talked about. And what I see here is that my classes are imbalanced, right? So there's 500 that have normal, 268 that have diabetes. So if you were to go through and create, say, a KNN model on this, and you were to do some model classification reports, so if you were to look at the performance metrics, there are some things you would see that might be a little alarming to you. So we know from before in class that a good metric for dealing with classification models is F1 score. You don't necessarily want to just look at model accuracy, and I'll explain that in just a minute. Okay, if you didn't already know. So moral of the story to start with is when you're working with classification models, you always want to look at F1 score, which is the harmonic mean of precision and recall, which we'll talk about what that is in a second. But all you need to know for now is that the model that we've created much better performs on the normal class when it's making classifications than it does on the diabetes class. And one of the things that could lead to a big difference in performance between classes is class imbalance, and that is what's happened here. Okay. So a couple things you want to think about when you're considering model performance metrics and class performance values and why you'd want to look at F1 score. So the accuracy score that you look at when you're performing a machine learning model right? So when you look at accuracy for the classification models, all that accuracy model is really doing is it's telling you how many predictions you've done correctly, right? So it's just looking at the things you've done right. It's not necessarily paying attention to the things you've done wrong. So because of that, here's an example that we like to give is look at spam. So email spam filters, right? Nobody likes getting spam. There's all these automated tools that can filter spam out based on specific things. So most of the emails that you get in a day are not spam. Maybe you get 3 out of 50, right? So 3 out of 50 emails you get in a day are not spam. So one way to come up with a model that tests well or that has an accuracy score that's really, really high is by simply having a model that just classifies everything as not spam. So if most of everything that comes through your email is not spam, and you have a classification model that simply says everything that comes in is not spam, it would actually be right like 95% of the time because most of the emails you get are not spam. So now imagine how that could extrapolate to being something bad. So for example, what if this was cancer screening? Or diabetes screening, right? Most of the people that we screen for diabetes don't have it. But what we want to do is catch the one that does. So it's important for your model to perform both on the do not have diabetes class as it would on the has diabetes class. Now, there are a couple different ways to measure performance when we talk about these things, because just because your model has a high accuracy score, it doesn't mean that it's necessarily bad. If it's got a high accuracy score, it could also have a high F1 score and a high precision and recall score. Let's take a look at those for a second. So when we talk about different metrics that you can look at to measure model performance of classification models, well, you've got measurements of true positives and false positive, which is some of the things that precision will do. And I'm kind of blowing through these because this is something that's covered in another video and we talk about it in class, and I'm afraid I'm going to lose my voice. We also have recall, which is also called sensitivity, that measures true positives compared to model predictions. But ultimately, what we really want to look at is the average of these things, or the harmonic mean of these things, which is the F1 score. That's kind of our big dog metric when we look at classification models. We want this F1 score to be high. We like this thing here, okay? So some things that you can do to improve your F1 score if you've got class imbalance is, well, obviously, before you create your classification model, you're going to want to balance your classes or balance the data. And that's what I want to talk to you guys about today, is how do you balance the data? So when you have class imbalance, you've only got a couple different ways to balance out those classes. And they don't have to be exactly dead on, but it's ideal for them to be dead on, right? So if we've got 500 people that don't have diabetes, then we would really like to have 500 people that do as we go through and train our model, okay? And we only want to do this on our training data, not necessarily our testing data, okay? So what are some methods that you can do? Well, you could go out and collect more observations, get more samples. That's probably the best way, right? Go out and collect real live data for people with diabetes to supplement the data that you already have. The problem with that is that's expensive. That takes time. That requires people to go out and actually collect. That assumes that there are more people that you have access to. So even though that would probably be the best way, right? Just go out and get more data. That's not necessarily feasible sometimes. So maybe there are some other things that we can do to go through and help with that. And that is where sampling techniques come in. Oh, pardon me. We will try to edit that out. That's where sampling techniques come in. So what are some things we can do with sampling techniques? Well, one thing we could do is something called oversampling. So what are we going to do? We're simply going to randomly select values or samples within your minority class, meaning the class that has less people in it, or less observations in it, and then we're going to simply duplicate them. So we're going to make more copies of observations in the minority class. That's called oversampling. We'll do that in just a minute. Another option would be called undersampling, right? So what is undersampling going to do? Undersampling is going to reduce the majority class to make it the same size as the minority class. So if we have 500 in our majority class of not diabetes and 268 in the class, the minority class, that means they have diabetes, we're going to reduce the numbers in the do not have diabetes category to reflect that 268. So in the end, you'd have two classes, both with 268 in them. The third option is something called SMOTE, synthetic minority oversampling techniques. And what that's going to do is it's going to create synthetic observation data points in your data to upscale your data and to make sure all your classes are equal. And it does that using the Euclidean distance algorithm or Euclidean distance formula to create these things. So now I don't want to spend a ton of time in PowerPoint. What I really wanted to do, which is probably what you're here for, is show you how to do this in Python, specifically in not sklearn. We're going to do this specifically using another library in Python called IMBLEARN. So there's a couple different things we're going to do here. So first thing we're going to do is we are going to bring in some portions of the IMBLEARN library. So the first thing we're going to want is oversampling. And from oversampling, we'll want random oversampling, and we will also want SMOTE, synthetic minority oversampling techniques. So the other technique we're going to do in just a second is we are going to grab undersampling. There we go. And from there, we'll bring in our random undersampler. Okay. So we'll just run that like so. Okay. So we've brought in two things. So what is IMBLEARN? So IMBLEARN is a Python library that is completely designed around simply balancing data sets. If you want to know more about IMBLEARN, you should be able to see this on my screen here, hopefully. Okay, there we go. From IMBLEARN, you would be able to go through and look through all these different things. So in this particular class, we'll probably only deal with oversampling, undersampling, and SMOTE, but there are a couple other variations in there that you can use as well as needed. Okay, so as always, everything we do in class, you can go to the documentation, right? We didn't make this up. We didn't create it, although I wish we had. So there's a ton of documentation out there if you need help along the way, including things that have code samples, and it'll show you the structure of all the things that we're doing here. Notice for this, we'll need to select our random state here. If we were using SMOTE, along with our certain number of neighbors to use in our sampling strategy. But for now, let's just start with the easiest option, okay? So before we do anything, we're gonna need to go through and we'll set our X and our Y values. So the first thing I'm gonna do is create our predictors. And in this particular case, how about we just use glucose, blood pressure, and say insulin. So we're gonna go, predictors are glucose, blood pressure, and insulin. So now at this point, I haven't done anything particularly special. I just created a list with the ones I wanted to use as predictors. So now what we'll do is we'll say our X value, right? Those are going to be our predictors. We're coming from here. And we'll say that our Y value is going to be DF outcomes. I think it's just called outcome. There we go. So if we were to look at just our Y, it should just be a series of ones and zeros. Perfect. So let's start with the first option, which is random oversampling. How are we going to go about doing that? Well, first we'll create an instance of the random oversampler like so. So we'll just go ROS equals random oversampler. And let's talk about how the random oversampler works. So what we're going to do is we are going to randomly duplicate values in the minority class. Okay, that's our goal, to randomly duplicate values in the minority class. So we don't want to just take them arbitrarily, meaning like we're going to start at the top and just copy them and paste them. So because we're randomly selecting values or observations to duplicate in order to balance the classes, we are going to want to set a random state here. And the random state can be pretty much anything you want. Like so, okay? So the next thing we want to do is we want to use this random oversampler that we've just created to oversample our minority class, which is diabetes. So how will we do that? Well, we're going to go X balanced and Y balanced equals ROS dot fit resample and we are going to give it our original X value and our Y value, and that is it. Okay, so let's talk about what I just did. Kind of like when you're using train test split, we've created two values here, right? So we've got X balanced and Y balanced. That's what we're going to use. So we're creating two variables that we're going to store data in. We're going to then call that random oversampler that we just created, and we're going to tell it to fit and then resample the original X and Y value data that we just created. Now here's what that'll do for you. So now if I look at Y balanced value, hey, look at that. Actually, that undersampled. Oh, shame on me. I was talking like random oversample, and I actually used random undersample here. So this is actually undersampled, but you know what? That's an example that we just used. So shame on me. I said random oversample. I typed random undersample. That's how it works. Okay. So it took the 500 from normal and it downscaled it to 268. Now we can do this exact same thing again, but we're going to do this with oversampling. So shame on me. So we can cheat really quickly to show you how to do this with oversampling. So I'm going to jump down here, and we're going to create our random oversampler instance, except this time we'll actually use the random oversampler instead of the random undersampler. So now, like I said before, with oversampling, because it's going to randomly select data and upscale it, right? So basically duplicate it, we need to set a random state. And we can just pick a random state, whatever you'd like that to be, okay? So from there, we can go through and do this exact same thing again, and in the interest of time, I can just copy and paste. Like so. And now, if we look at this, so if we do Y balance this time, actually, you know what's going to happen? There we go, 500. Oh gosh, we'll have to edit that out again. I apologize, friends. I'm still getting over that cold. So these two techniques we've used so far, we have undersampled our data and we have oversampled our data. And one more time to make sure you get it. So when we undersampled, we randomly selected values of the majority class, which was does not have diabetes, and we simply removed them. And we're not going to use them. So now those classes are not imbalanced. Okay. Down at the bottom here, we did the same thing in reverse. So we randomly selected values in the minority class and we oversampled them. So now they're equal in this way. So the last thing you can do is SMOTE. So SMOTE is a type of oversampling. It's just doing it synthetically. So why do we care about that? So the challenge with oversampling is that oversampling infinitely grows your data because you're copying it. So whatever you've got in there is just going to keep getting bigger and bigger and bigger and bigger and bigger. What SMOTE does is it does something similar, but it does it all synthetically using Euclidean distance and k nearest neighbors. So it's going to look at observations and it's going to try to create synthetic plots next to those that basically duplicate the ones synthetically instead of actually just copying them. Okay. It's our friend. It's a good thing to do. But SMOTE can be slow. And it doesn't work really well with big data that is severely imbalanced. But let's look at how we can use SMOTE. So we're going to create an instance of SMOTE, like so. So now with SMOTE, you have the ability to go through and you can actually set your sampling strategy if you so choose. I don't really want to touch too much on the sampling strategies. For now, let's just say you still have to set a random state. And it can be anything we want it to be, like so. Now, once we set that random state, we're going to do much the same thing we did here. Okay, except this time, we will use SMOTE instead of random oversample or random undersample. So now when we do this, everything seems to be run correctly. Let's see how it goes. So if we were to go through and do our value counts again, I bet you can figure out what's going to happen here, right? So if I do my Y balanced, and there we have it. We are balanced, Okay, so we like this. So quick reminder on why we like this. I want to explain this one more time and I'll let you get out of here. So the reason we need to balance our classes when working with classification models is the model will weight or perform better on the class that is the majority. So the more samples you have, the majority class will perform better historically. So in order to balance classes, the easiest way to do it is using IMBLEARN if you are working with the class with me. So with IMBLEARN, you have the ability to undersample, oversample, or use synthetic minority oversampling in order to balance our classes. And in the end, you come out in the same place. It's not horribly difficult to do. It won't take you a ton of time, but I do want to tell you that you would want to do this only on your training data and not on your validation data. Okay, which means that you would do this after you partition your data if you were actually making a model. So with that, I do think I'm going to lose my voice completely, so I just wanted to get something out because I know homework is due tomorrow, so hopefully this gave you a few hints of some code that you might be able to use in order to get you through. With that, my friends, I will let you go, and I look forward to talking to you soon.